All right, Tom, are you ready to go?
Yep, I am ready to go.
All right. You got the ability to share your screen?
Yes, I do.
All right, begin.
Let me get this shared. Okay. Everybody see the visual astronomy slide?
Yes, we see it.
Yes.
Okay. Let me start off. Some of this material you will have heard before, but I think it bears repeating. I'm going to talk for about 30 minutes here. I'm going to talk about visual astronomy, which to my mind is probably the more fun part of astronomy. Okay, let's see if we can advance the slide. Why doesn't that want to advance? There we go. All right, now we're cooking. Let me back up a little bit. Visual astronomy, as we're going to define it and talk about this morning or this afternoon, is looking at the sky with no electrons. Doesn't mean you can't use your cell phone, and we'll get to talking about that later. But nothing in the optical path. Just you and the stars looking at one another through either directly or through a telescope. You might ask, okay, why would we want to do that? Well, the first astronomers did it this way. We'll talk about them a little bit. They had no electronics. They had no photographic technology or capabilities. What they could do was look at the sky and write down what they saw, or perhaps draw pictures. You could do this with as little equipment or as much as you might want to have. Everything from just putting a blanket out on the grass in your backyard and laying down, looking up at the sky, all the way up to building your own little observatory in the backyard and installing several tens of thousands of dollars of equipment so that you can see everything that's up there. There's a lot of things to see and do visually, and it's lots of fun. You can take your whole family and you can point out and say, oh, look at that over there, and everybody can look at it and say, oh, yeah, I see that. Originally, and you see this up in the upper left-hand corner, shepherds, people, that spend their nights out in the dark, underneath the stars. They would look up in the sky and they'd look at patterns and they'd see the stars and say, that pattern reminds me of whatever. And you do this with clouds, you do it with stars. Everybody has a good time. We have that brought down to us throughout the ages as constellations. And there's a lot of favorite constellations and a lot of famous constellations. We'll mention those a little bit later. Later on in the Dark Ages here in Europe, you had Arab astronomers. And you see that in the lower left-hand corner. He's got a measuring device that tells him what the angle is of a particular star he's looking at. And he's probably got a scribe that he tells, okay, and he writes down what the numbers are. They cataloged the stars. They marked down which ones they thought were brighter and which ones were dimmer. And they talked about where the planets were and how the planets moved and what the moon was doing. Up until about 1600, that's what you could do. 1600 was the first time that Galileo Galilei put a telescope to his eye and looked at the heavens and saw more than you could see with your own naked eye. The two statues you see there, Tycho Brahe and Johannes Kepler, are just about the end. They were doing their work around 1600, and Brahe, the one on the left there, was an astronomer. He looked at the skies and he measured things and he wrote them down and he took great notes. Kepler was a mathematician, astronomer. He looked at all of the data that Brahe had put together, and he was the first one who decided, you know, I can put together a mathematical formula that tells me what the orbits of the planets are. And we still roughly use the same stuff that Kepler noticed in Brahe's observations. We call them Keplerian orbits for planets and for moons around planets. Right at the end of this, right at the beginning of the 1600s was when we began to use telescopes. And what you see there in the bottom, in the middle, is a drawing of what was called a monster telescope at the time. That thing was 40 feet long and 8 feet in diameter. It wasn't easy to move, but it sure did give images of the heavens that let you see a lot of things that you couldn't see before. But the emphasis is on seeing. So when we talk about no electronics, it means using your eyes with no digital camera to capture an image. Okay, we'll relax that a little bit later on when we talk about eyepieces. It doesn't rule out aids such as your smartphone sky maps or a computer-controlled telescope. I have both. I don't do astrophotography, and I don't use cameras very much, but I do use computer-controlled telescopes, and I do use my smartphone for the sky map. Okay, doing it with no electronics makes the activity a good bit less expensive, and I believe more fun. The color photos you see in magazines and on TV require an awful lot of wait time at night for the electronics to do whatever it is the electronics are doing. Plus, afterwards, you spend a lot of time at the computer doing cleanup of the picture, doing enhancement of the picture. There'll be people talking about later on in the afternoon, talking about doing photography and the kinds of things that you need to be able to do to get a nice picture. I think with visual astronomy, you will end up, or excuse me, with photographic astronomy, you'll end up seeing less of the total heavens, and I believe you have less fun. It's an awful lot of work to use those electronics while you're trying to do a fun evening doing astronomy. Okay, to begin with for visual astronomy, the first thing you need is a dark sky. City skies aren't very dark. All you're going to see is the moon and maybe some of the planets. You really need to go either up to the observatory or some other not dark location, not in the city. I think we talked about earlier some of the dark sky sites that we have around here. You don't have to go to a really dark site. You don't have to go very far, but you do need to get out of the city. Okay, the second thing you're going to need is a sky map. And here we're talking about the paper kind of sky map. This lets you find stuff on a piece of paper and say, yeah, that's about where it's supposed to be. The smartphone apps that you have and can use, and I do use, they're really good at identifying. You hold them up in the sky and you point it over there and say, what is that bright object? And it says, ah, that bright object is Mars. That's great. The trouble with those smartphone apps, they're not very good at finding what you want to see. If you didn't know that there was that bright point up in the sky and you hold up your camera or you hold up your smartphone to look at it, you wouldn't know that it was Mars. If you just hold it, I want to find Mars, and we'll say, okay, Mars is somewhere. You would know that. Okay, the last thing you're going to need is a book. And the kind of book we're talking about here is a book for beginning astronomers, or even for accomplished astronomers, about what there is to look at. One of the things that you just saw in Mr. Cassidy's presentation was, and some talking about what's available to see in the night sky tonight. And that's the kind of thing you really need to have in order to be able to enjoy. Let's see, tonight we're going to go look at the Andromeda Galaxy. And here in the book, it gives you instructions on where you should look and how you find the Andromeda Galaxy to be able to look at it. Fourth thing we recommend is a membership in the Astronomy Club or Society. And hint, hint, we're talking about our society here. Okay, what kind of book you need? The book tells you what's in the sky to look at every night and where you need to look. The two books that we also recommend to quite a few people are called 365 Starry Nights, and the other one is Turn Left at Orion. Both of these are coffee table kind of books that you can look at during the day and say, yes, I think I want to look at that tonight, and this is how I'm going to find it in the night sky. You can satisfy your paper map and book needs with a subscription to one of our astronomy magazines. Two such magazines that I use and a lot of us use are Astronomy and Sky and Telescope. Both of these have a centerfold map each month that shows you what's in the sky and what's moving in the sky for this month. Both of the magazines have websites with a lot of resources. Okay, this is the cover from the two books that we recommend: 365 Starry Nights by Mr. Ramo, and Turn Left at Orion by Mr. Colsomano and Dan Davis. Both of them are excellent books, and neither one of them will disappoint you, I don't believe. I actually own both of them. These are the two magazines, and they are very similar in, I guess, similar in what they're going to cover, because both of them talk about this month's stuff or things that have happened recently. They are slightly different in their approach. You're going to find Sky and Telescope is a little more scientific and scholarly in its approach to things. Astronomy is a little more popular and a little more, here's the fun things to look at. So you got your choice of, if you just want one of them, I would recommend going with Astronomy. I think that's a more fun magazine to read. Sky and Telescope, I have subscriptions to both, but Sky and Telescope is a little more scholarly and a little more detailed and technical in the information that they present to you in the various articles inside the magazine. So, time to begin. You ready to go out and stargate? What can you see just going outside, knowing you've looked at your book and you know where you want to go look and see things? You can see stars, North Star, and Betelgeuse. There's an asterisk on Betelgeuse there because Betelgeuse, that isn't the way you spell it, but that's how we call it. It's really Betelgeuse, and it's an Arabic term and translates as the armpit of the giant. So whatever, Betelgeuse. You can see constellations like Orion and the Big Dipper. There's an asterisk on Big Dipper because that's not really a constellation. I think Mr. Cassidy covered that a little earlier. The Big Dipper is what we call an asterism, a star picture in one of the constellations. Everybody calls it a constellation. I've got it here as a constellation. What the heck? You can see clusters of stars, like the Pleiades and the cluster in Hercules. You can see the Pleiades on just about any night. And sometimes you can see it, it's actually bright enough that you can see them from the city, in the city sky pollution, light pollution. Cluster in Hercules, you're not going to see until you get out in the dark sky. But both of them are clusters of stars. Most of the stars that you see in our galaxy were born in clusters. And over the millions of years, those clusters begin to drift apart. Pleiades and Hercules have not drifted apart yet. They're still young enough that they're grouped together and they look like a clump of stars in the sky. You can see galaxies. Now we're still looking with just our naked eyes. You can see galaxies, ours and the nearby Andromeda galaxy. One of the things that you heard earlier was how much bigger the Andromeda galaxy is than the full moon. Well, that's true, sort of. It's bigger, it's actually physically bigger in the night sky if you're looking with the electronics. If you're just looking at it with your eyes, it's going to be a fuzzy patch. But it's interesting to find. And I was astounded the first time I saw it with a naked eye, and I saw it up there at VBAS. And you just look up there, what is that? I said, oh, that's the galaxy. Another thing you can see is comets and meteors. And there's two meteor showers. Ms. Cassidy talked about the meteor shower going on in October, the Orionids coming from the constellation of Orion. There's two coming up in November and December, the Leonids and the Geminids. Leonids are a meteor shower that appears to originate in the constellation of Leo. And the Leonids run the the entire month of November, and the peak nights are going to be the 16th and 17th. The they're actually the remnants of a comet. And what happens is the comet goes on its orbit around the sun, and the tail of the comet that you see coming out behind it is actually bits and bobs of dust and gas and whatever. And when the Earth runs around it through its orbit, it goes through the place where that comet went by earlier. We pass through all of these bits of dust and everything, and they show up in our night sky as meteors. So that runs the entire month. The comet that they're associated with is called Tempel-Tuttle. Don't know that that's really important to you. The meteors that you're going to see there aren't going to be a lot of them, but they'll be bright, and they tend to have tails that last a little bit in the sky. So it won't be just a quick across the sky. The meteor will go across, and then there'll be a glowing tail that gradually fades out. The second group we're talking about here are the Geminids. The Geminids are pretty impressive. They run the first half of December. They are not associated with a comet. They are associated with an asteroid. And the asteroid is called, let's see, Phaethon. And Phaethon asteroid gives you very bright meteors. So the Geminids in December, the Leonids in November. So there's a month and a half of comets and asteroids providing us with meteor showers in our night sky that you can see with just your eyes. Okay. Here we see some photographs, and I apologize, but I got to show you photographs even though we're talking about visual astronomy. The upper left you see there, the very bright thing is the planet Venus. The other stars that you see, the ones that look kind of like a very teeny tiny dipper, that's the cluster of the Pleiades that I was talking about earlier. And those stars are actually close together in the night sky and in the galaxy themselves. They are clustered together. Interesting to see. The Pleiades are something that have been seen and talked about and mentioned in almost every culture. That particular set of stars has always been a object of attention in the night sky. The upper right is a constellation. That's the constellation of Orion. You can see the red star at the top. That's Betelgeuse. And then that's one shoulder or armpit. And then there's another shoulder or armpit up the top. And you go out down to the bottom, there's a couple of knees. And in between, there's a 3-star group called the Belt of Orion. And below the belt there is the Sword of Orion. You look at that star in the middle of the Sword of Orion and you say, something's wrong with that star. Well, that's true. That's not really a star. That's one of the nebula we were talking about. That's called the Great Nebula in Orion. You can see this with your naked eye. It is not as noticeable as it is here in this picture with your naked eye. But here in just a minute, we're going to talk about some optics that'll get you closer and make it more interesting. That's a nebula. So you can see a constellation and a nebula. The red things that you see there are stuff that you have to have the photography to be able to see. Those are actually glowing clouds of hydrogen. And it glows red because that's what hydrogen glows as. You won't see those with your eyes. You will see those only in photographs. Lower left is another galaxy. That's our galaxy. That band of white running across from the bottom to the top. That's our galaxy, the Milky Way. If you look at it at night with your eyes, it's going to look kind of like somebody spilled milk up in the sky. The streaks that you see, the white streaks, that's a meteor shower coming out of what looks like the middle of the Milky Way. Actually, I believe those are Orionids, the ones that are going on right now. And because you can see down there in the lower right-hand corner of that photograph, the constellation of Orion with his shoulders and knees, belt and sword. Okay, in that picture, if you look at Orion and you look at his belt, and you look up from the belt, there's sort of a red star and a little V. Okay, that red star and that V is part of a constellation called Taurus. And that red star and the V are known as constellation, the face of the bull. Taurus is a bull, and the red star is one of his eyes. If you keep going up, there's what looks like a large star. That's the asterism, the group that we call the Pleiades. And you can see that's fairly bright. So Orion, Taurus, and the Pleiades, all in that picture with the Milky Way and a series of comets. All of these things you can see with your eye. If you look over at the bottom right photograph, what you see is a picture of comet Neowise. That's the comet that we saw here earlier in the summer. And there's a picture of it when it was working towards its, it was on the way out, because it's way up north. It's next to the Big Dipper. And you can see the Big Dipper in that photograph. You see that with your eyes. It's difficult to see in this photograph, but with your eyes, you'll be able to see the middle star in the handle of the Big Dipper is actually 2 stars. That is a double star. You can see that double star with your eyes. In the night sky with your eyes, you will see the bright star, and then you will see a dim one next to it. You can't make it out in this photograph, but you'll be able to see it with your eyes. That's one of the problems with photography, that your eyes are actually better than a photograph. Same problem with how Venus is so bright in that upper left photo. That's because the photography is kind of very difficult to capture a range of brightness from the dimmer stars to the very bright planet. And here we are from the bright comet to the dimmer stars up in the Milky, in the Big Dipper. So your eyes do better than photographic work on those kinds of objects. Okay, moving on up, equipment. If you want to see more stuff that's in the sky, you're going to need some optical power. First, you don't really need magnification as much as you need more brightness. Things that are dim, you want to make them stand out. You need more brightness. You need to capture more photons. And that's going to make everything like galaxies, nebulas, clusters, all this, it's all going to look better with more brightness. Professional astronomers need lots of brightness. So that's why they need the really big telescopes. You won't need the really big telescopes for visual astronomy. All those dim smudges in the sky are going to turn out to be interesting objects to look at. And let's talk about some of this, some equipment. First telescope. First telescope we usually recommend to people is a pair of binoculars and a lounge chair. Not a lot of investment required, but binoculars are easy to use and find what you're looking for. You can see something in the sky and then lift the binoculars up to your eye and there it is. One of the most difficult things that beginning astronomers find is experience. It's finding things in the night sky with their new telescope. Not so much of a problem with a pair of binoculars. Also, while you're lying there in your lounge chair, you can lower the binoculars, just look at the night sky and say, oh, look at that. That's a satellite going over. You're not going to find any satellites with your telescope. With binoculars you can, and with your bare eyes you can. Binocular technology. I'm going to go over this again. Mr. Sitowski talked about this a little earlier. Binocular technology, they give you more light and sub-magnification. What we recommend to you is probably something got marked 10 by 50. And the 50 talks about how much more light you get. That's the diameter of the front lens. Your eye is about a 6. That's the diameter of the pupil in your eye. The 50 gives you 50 over 6 squared, or about 65 times more light, more photons that you capture. You don't get quite that much benefit out of it because you're going to do some things with those photons that your eye doesn't do. The 10, which you see in the 10 by 50, is the power of the binoculars. And you don't have to have a 10 power. I have a pair of 10 by 50s. I also have a pair of 8 by 35s. More than 10 power is hard to hold still. The image seems to jump around. It's hard to hold things still where you can enjoy looking at something in the night sky. It will help if you're in your lounge chair with your head braced against the back of the chair. But we have larger binoculars at the Society, which you can come up and look through, and you can notice just how difficult it is to hold the binoculars still enough to really look at something in the night sky. Now the 10 power actually reduces the brightness of your image, but also the sky around your object looks darker. So you get better contrast. You end up with a much nicer picture, a better image with a little bit of magnification, 10 power, and a lot more light. And things like the nebula in Orion are going to say, ooh, look at that. That is obviously a nebula. Okay, so this is what you're going to have. You're going to have a pair of 10 by 50 binoculars or similar. You're going to have a lounge chair or similar. And you're going to have a book. We recommended one of those 2 books that you might have. And also your map. So that's going to be your beginning activities. Don't buy binoculars with the red lenses on the front. What those are binoculars that they've skimped some on the price of the lenses inside. And in order to make it appear to be sharper, they take the red light that's coming into the front of the binoculars and reflect it back out. That's why the front of the lens looks red, because the red light being reflected from the binoculars. Okay, without the red light, just the green and the blue coming through, your eyes can focus it, and the lenses inside the binoculars can focus it better. You get a sharper image. Buy the ones who have either no color or sort of a greenish color on the front. The greenish color is a scratch protection and an anti-reflection coating. Don't buy the ones with the red lenses. Okay, your really first telescope. After you've seen everything that you think you can possibly see with your binoculars, you're going to want to buy a telescope. Things like the Orion Nebula, craters on the moon, all of these things are going to look much bigger because with the really first telescope, you can get a lot more magnification. Now, I'm going to go over this real quick about the kinds of telescopes and this kind of thing. Later on in the day, Mr. Jeff Delmas is going to talk about telescopes. He'll give you a lot more information about what kinds you need, how they work, and this kind of thing. Basically, there's 3 kinds of telescopes. The refractor scopes that have the lens in the front. That's the one that you see that has a long tube and an eyepiece at one end and a lens at the other. Reflectors, which don't have a lens at the front, what they have is a mirror at the back to collect all of this light and focus it down. And a catadioptic, which has both a lens at the front and a mirror at the back. Any one of the 3 will work. Any one of the 3 will give you years of fun. You will get the biggest bang for buck with one of the reflectors. And the reason for that is it's easier for the manufacturers to grind one surface and make a very good mirror than it is for them to grind several surfaces to give you a good lens for the front. So bang for the buck, you go with reflector. I will admit I have at least one of all 3 types. I find the mirror ones, I can afford a bigger telescope. Need to move on here. Here's pictures of the 3 kinds. Upper left is a refractor, got a lens at the front, eyepiece at the back. Upper right is a reflector, got a mirror at the back, which you can't see in this picture, and an eyepiece at the front, and a catadioptic there at the bottom. It has a very thin lens, which you can just barely make out there on the front of it. Also has a mirror at the back, which you cannot see. Okay, which do you need? Depends on what you want to see. If you're looking at moons and planets, you can see any of the things that you want to see on the moons and planets with a scope about 6 inches in diameter or larger. You're not going to want to afford a refractor telescope 6 inches in diameter or larger. You'll end up with a smaller refractor probably. To see faintest objects like the Ring Nebula, you need a bigger telescope to gather more light. Don't buy one over 12 inches. That's about as big as you're going to be able to move around by yourself. We've got some larger ones at VBAS. It takes 2 people to move the larger ones. The 21-inch doesn't move at all. It stays mounted inside the observatory. Okay, computer motor aided. You might want to buy one of these. You might want to think about it. It's going to increase the price, but it's useful. It's a good thing you can do with visual astronomy, because difficult thing to do with a telescope is finding something. You know what you want to look at. You've seen it right there in the book. You just got to be able to find it. Okay, the problem that you're going to be able to do. The second problem is the target's going to start sliding out of the view towards the west. You know, because the Earth rotates east, it looks like the stars are going to slide to the west out of your telescope view. A motorized mount will track the target. A computer-controlled motorized mount will solve both of these problems, because you can tell the computer what you want to go look at, and it will slew and find that object, and then it will keep track of that object and glide the telescope to the west as the star moves to the west. I recommend that you go ahead and do the computer-aided telescope. Here's a picture of a computer-aided telescope, the orange one in the upper left. That one's by Celestron. There are several other manufacturers. And that's the computer. Comes with it. Got all of the stars and planets and everything inside the computer. And you determine on the screen, tell it what you want to go see, and it will move the telescope and point at that object. What you see in the lower right there is the motorized. This one is one that has a single motor that will turn the telescope and make sure that whatever you're looking at, it will track it as it slides to the west. You still have to find things by hand. Eyepieces. Going to need some eyepieces to go with it. The magnification of your telescope is decided by the eyepiece. Smaller number on the eyepiece means more magnification. Use the eyepieces that come with your telescope. Until you decide that there's something wrong with that eyepiece, it doesn't give you the crisp view that you want, it doesn't give you the wide enough view that you want. Don't buy any more eyepieces until you've decided what you want to buy. Then talk to some people about what their eyepieces will show. Let them try to use one of their eyepieces in your telescope to see if it's really going to work for you. There are adapters that you can use to attach your smartphone to an eyepiece. You can go semi-digital photographic. You can do a little bit of electronic if you really must. Interesting stuff if you take a picture of the moon. That's, you know, a neat thing to do. That's all of the electronics. Here's a picture of 3 eyepieces. These are not expensive eyepieces. All three of these have smaller numbers. You see the one on the lower left is 4, lower right is 6, and the one at the top is 9 millimeters. You're going to want something bigger than 9 for your telescope, probably 20 or 25. The 25 will give you a bigger field of view, but smaller magnification. Okay, what can you see with your new telescope? You can see a lot more detail on the moon and planets. With your binoculars, you saw the planets were disks. With this new telescope and your eyepieces, you're going to be able to see things on Mars, and you're going to be able to see the bands of Jupiter. You're going to be able to see the rings of Saturn. You're going to see more planets. Uranus and Neptune can't be seen with your naked eye. You need to have a telescope. That's why they weren't discovered until after the invention of the telescope. Okay, outside of our solar system, you're going to see a lot more star clusters, and many of the stars that you're looking at are suddenly going to become a double star. You're going to look at it and say, oh, look at it, a double star. A lot more nebula are going to appear, just like it's going to be like magic. You can see nebula that you've never seen before. This is a picture of the Orion Nebula that I talked about earlier. You're not going to be able to see it quite this bright unless you get up to around the 12-inch telescopes. But this you can see by eye. It's not going to look red. It's going to look green when you look at it visually. The reason for that is because your eye is sensitive in the green, much more sensitive than it is to the red. The photographic work that you can do, you can just color it red if you like, because it really is red. It's glowing hydrogen. It's going to look green to your eye. You can get better books. Now that you have more telescopes, you need more targets. The Society Library, you did join, right? Will have more and better printed materials to describe the sky. There are national and international societies that have observing projects you can complete. One of them is the Astronomical League, and they have things like the Messier list, named for a famous French astronomer. It's a list of over 100 objects that you can look at and see visually with your telescope. He compiled the list with about a 4-inch telescope. Named for that famous French astronomer. It's actually a list of things he didn't want to look at anymore. Sooner or later, you're going to want to see more, and that means a bigger telescope. The first problem you're going to find with your new, bigger telescope is explaining to your spouse why you need another telescope. And it's an additional telescope, not a replacement. Alternatively, you can join a club or a society, hint, hint, and use their larger scopes. We have larger scopes at the society in the observatory available for you to use if you're a member. This is the kind of things you're going to be able to see with your larger telescope. What this is a picture of the moon with Mars coming out from behind it. The moon has been in front of Mars, and now moon is sliding out of the way, and you can see the moon and Mars. You can see this visually with a telescope. You'll be able to see comets with your telescope in much more detail. This is a picture. This is 5 different looks at the various comet Neowise that we were looking at earlier this year. The lines are pointing towards where the sun was actually located down below the horizon. You can see the dates when you could see it at those positions. You're going to be able to see a lot more meteors. These are Perseids, which occur in August. You're going to be able to see a lot more nebula. This is a very famous nebula. The red one there is called the Trifid Nebula because it looks like it's got 3 parts. To the right of the Trifid Nebula is another star cluster, one that you would never have seen with just your bare eyes, your naked eyes. And here's a picture of our favorite asterism, the Big Dipper. If you look at the handle of the Big Dipper, the star in the middle of the handle of the Big Dipper, you can see through this picture, you'll see this in your telescope. It's actually a double star. You can see that bright star just up to the right of there. If you magnify it, you'll see something like this. Okay, I don't have a picture of it, but you can see with your naked eye, with your telescope and your visual astronomy, you'll be able to see that that bright star is actually 2. So you're not looking at 1 star, you're not looking at 2, you're looking at 3 with your visual astronomy. That's what I've got, and if there's any questions, I'm glad to answer.
All right, thank you, Tom. Tom is, of course, a past president of VBAS, and we're running a little behind on time, so if we have one question, anybody have a question?
Let me get rid of this.
All right, okay. Thanks again, Tom. That was a great presentation. I really appreciate it. Next up should be Mitzi Adams. Mitzi, are you on?
I'm here.
All right, Mitzi is going to do a presentation on solar telescopes and solar observing, and I will turn it over to you.
Okay, hang on. Can we just hold on a second here? I want to reset the video recording again.
Okay.
And I'm getting a note that the host disabled attendee screen sharing.
Okay. Hang on a second here. All right, so we're recording, and I will, okay, Mitzi, you should be able to do it now.
Okay, yeah, it looks like I can. And there we go, I think. Do you see the title slide, Observing the Sun?
How do we know what we know?
Yes.
Okay. I'm Mitzi Adams. I'm actually a former planetarium director. That was, oh gosh, 15 years ago now, I think, when I ended that tenure. But I'm a solar scientist at NASA Marshall and the NASA liaison to the Von Braun Astronomical Society. So we're going to talk about the sun and some solar activity. You're always told never look at the sun. Well, we had kind of hoped that we could provide you with some live observing of the sun with a special telescope that looks at one layer of the solar atmosphere, and we'll get into that in a little bit. But you see why today would not be a good day to try to look at the sun with the telescope. And I want to reiterate that you should never, ever, ever look at the sun with your unaided eye, and only with a telescope that you know has the proper lenses for safely looking at the sun, because you can very, very quickly lose your eyesight if you look at the sun and the light is focused onto your retina. Okay, so the sun itself is seen in this picture from the Solar Dynamics Observatory, and you see some spots on the sun, and those are called sunspots. We're going to get into that in a little bit. The sun is the largest thing in our solar system. It has about 99% the mass of, or the total mass of the sun, of the solar system. It's composed mostly of hydrogen. It has some helium and other components. It has a very hot core temperature, and that temperature decreases as you get to the outer layer of the sun, the photosphere, which is what you're seeing here. So the sun has an inner core, which is where the energy is produced by thermonuclear reactions. And obviously, this is something you cannot observe with a telescope. And either from SDO, which is in orbit around Earth, or with any other telescope that's located on Earth. We have inferred this from observations of the sun through many, many, many years. But it has a central core, and around that core is a zone called the radiative zone, and then the convection zone. And that then from the convection zone, we get to the photosphere, which is called the surface, which is where you see sunspots. Above that is the chromosphere. The chromosphere is a relatively thin layer of the sun, of the sun's atmosphere. It's an area where hydrogen absorbs energy and radiates radiates photons in a very specific color of light called hydrogen alpha. And there is a solar telescope that we would have been using live today that would have given us views of the chromosphere in the light of hydrogen alpha. And this is an important layer of the atmosphere to observe, because sometimes we see very, very bright explosions in the chromosphere. These are called solar flares. And you're going to see why in a couple of more slides, why solar flares are important. But we see those flares in the chromosphere. They're linked to the magnetic field of the sunspots in the photosphere. And then we have the upper layer of the sun's atmosphere, the corona, which actually reaches all the way out into the solar system. We're in the corona. But of course, it's very different when you're close to the sun. So the sunspots, as I mentioned, are dark spots that we see in the photosphere. They are cooler regions, and they're cooler because of the magnetic field that's associated with them. They're actually quite large as compared to the Earth. You can actually see the Earth next to, or the size of the Earth next to one of these spots. And so sunspots can be as large or larger than Earth. and they have been observed in one way or other since Galileo first used his telescope, his early telescope, in around 1609. And the way that we had imagery of the sun at that time was that people would draw what they saw. And as a result of observations, many days and years, Galileo determined that the sun rotated once in about 27 days. And there was a big controversy about whether sunspots were actually part of the sun or whether they were above the surface. And there were letters written back and forth between Galileo and Christoph Scheiner, who was a Jesuit priest. And Galileo got into a lot of trouble because of his views on the sunspots. And he apparently had kind of a big mouth and got in trouble with the Pope at the time. So the sunspot structure in the photosphere is basically a bar magnet. And there are regions where intense magnetic fields break through the surface. And because of this magnetic field overlying the surface, the spots are cooler than the surrounding region. And the sunspots' magnetic fields are similar to the magnetic field of Earth, why it's like a dipole magnet. But the magnetic fields are really important because the magnetic fields confine gases, plasma, and when the magnetic field is strong and the field dominates, which is what happens in sunspots, then the magnetic field pressure dominates what happens. But then as you get above the sunspot, and the magnetic field is not quite as strong, then the gas pressure dominates, and then the magnetic field follows the gas. So let's see. We've observed the sun with telescopes from Earth since Galileo in the 1600s. And then we began putting telescopes in orbit around Earth and around the sun. Of course, the Earth is in orbit around the sun too. But in 2010, we launched this telescope, the Solar Dynamics Observatory, and it began making observations of the sun every single day, 24/7, 365 days of the year, and sending us back data. We now have a complete solar cycle of observations from the Solar Dynamics Observatory. But this is a little introduction to what the Solar Dynamics Observatory SDO has shown us, or sort of an overview of SDO. And then we're going to talk about the solar cycle itself.
You know you're not supposed to stare at the sun, but who could resist a peek at this? A new NASA spacecraft called the Solar Dynamics Observatory, or SDO, will deliver startling images of the sun with 10 times more detail than HD TV.
Our mission is to study the sun. We have 3 instruments that look at the sun 24 hours a day, 7 days a week, and send down data.
The goal of the mission is to help scientists zoom in on solar activity, such as sunspots, solar flares, and coronal mass ejections, thus improving forecasts of solar storms.
The sun puts out what we call space weather, bright flashes of lights that we call flares, particles, which we call radiation here on the Earth, that come and affect both our satellites and our astronauts.
And that's just the tip of the iceberg. Electrical power to our homes, satellite communications, and navigation systems can all be disrupted by solar activity.
The sun is our closest star. It affects our life on Earth more than anything in the universe.
SDO will provide a close-up look at the sun that you may not be able to tear your eyes away from.
And there are many, many, many more animations from SDO that show 10 years of observations with the telescope and show how the sun has changed over that 10 years. So let's go back to when astronomers were just using telescopes or without photography. But then they start, they used drawings to draw these sunspots. Astronomers were observing sunspots over many, many, many years. And then an amateur astronomer, Heinrich Schwabe, discovered in 1844 that sunspots would increase over time, and then they would reach a maximum number, and then they would start to slowly decrease. And this is what we call the solar cycle. It's a buildup of spots on the surface of the sun. That is, you look at the sun every day and you count the number of spots on it. And of course, that changes day by day. And the solar cycle is that cycle of activity when the sun goes from very few spots in solar minimum to quite a few spots at solar maximum. And then you see there's also the number of spotless days that he discovered. We now have 23 cycles, full cycles, plus some more. We are at solar minimum in 2020. I'm showing you data from David Hathaway, who retired from NASA, and he has, with his former graduate student, created another website called Solar Cycle Science, where he has plotted the data all the way out to 2020. So if you're interested in seeing what the cycle looks like now, you could go to solarcyclescience.com/solarcycle.html. But back around the time of the launch of the Solar Dynamics Observatory, we had a maximum number of sunspots. And we are now in solar minimum when we have very, very few sunspots, like just before the launch of SDO. We have sunspots that appear to come onto the surface latitudinally. That is, at the beginning of the cycle, they'll appear in the higher latitudes, around 30 degrees north or south. And as the cycle proceeds, they move towards the equator. And this is called a butterfly diagram. Again, this is from Dave Hathaway. Thank you very much. And the cycles themselves overlap by a couple of years. There is a polarity law that was discovered by Hale. And this polarity law relates to the polarity of the sunspot magnetic fields. So what I'm showing you here is a map of magnetic field intensity. And the blue is one polarity of a sunspot or an active region. The yellow is the opposite polarity. So I don't remember which is which, but blue is probably negative and yellow is probably positive. Now, if you look at those sunspots that are in the southern hemisphere, the polarities are reversed. So here you have yellow on this side of the sun and blue on this side of the sun. This is called the leading polarity, and this is the following polarity. So the leading polarity here in the north is negative, and here in the south, it's positive. Now, when you go from one cycle to the next, those flip. So the solar cycle, part of that is to flip the polarity of the sunspots. And then you have the tilt. So when the sunspots first appear on the surface, the following sunspot, so this is the leading sunspot, this is the following sunspot, the tilt is much less. And then as the sunspots mature, the tilt will increase. And then with different active regions, you will see a change in the tilt angle with latitude. Now, Dave Hathaway put together a movie over a cycle or so, a cycle and a half, and you can see how the polarities flip. Remember, this is the leading, this is the following polarity. Here, this is the leading polarity, this is the following polarity. And this is a positive, this is negative. Here, the leading is negative and positive in the southern hemisphere. And as you get to the next solar cycle, those polarities will flip, and you'll see that then the leading in the northern hemisphere will be the blue color, and the leading in the southern hemisphere will be the yellow color. So what he's done is just take that central region between 30 degrees north and 30 degrees south, peel it off, and take a look at how things change over the cycles. So you can see definitely that solar minimum. Let's look at it again. And you can see how the sunspots appear and disappear with the cycle. So there are lots of spots. Then you go through a minimum number of spots, then a lot of spots, and then a minimum. And then there was a minimum around 2009. And then we had a maximum around 2015. And as the cycle continues, the magnetic field tends to drift towards the pole. And so as the cycle continues, the magnetic fields will drift towards the pole. When you have a shift in the cycle, these the polarities actually cancel out, and you get a change from one polarity to the other when the cycle begins. Now, I mentioned before that I was going to talk about some of the effects of the sunspot cycle. Why do we care? Why do we make these observations? Well, there are these explosive events. I mentioned solar flares that we can see in the chromosphere, see happening in the chromosphere. And sometimes these lead to very large bursts of energy and particle ejections that we call coronal mass ejections that can interfere with our satellites, with our GPS. They can cause radio blackouts. As a matter of fact, there was a geomagnetic event. This is how the Earth responds to these kinds of events that happened during President Nixon's flight to China, where he was actually out of radio contact for 4 hours. That's been a while back, but you know, that would kind of make one worry a bit. Let me go back to this one for just a second. So the brightening is called a flare. Now you see all of the noise in the detector that you're seeing there. That's from the particles that are streaming out from the sun, interacting with the detector. This is no longer SDO. I wonder if I can go back to that. This is an instrument called SOHO, or the Solar Heliospheric Observatory. And it has, this is another way of observing the sun, a very special telescope that creates an eclipse all the time. And the eclipse is caused from something called an occulting disk, and that's what this circle is. And this is the smallest they can get it with the technology that we have. So you see, this is actually the surface of the sun. There's a section of the solar atmosphere from the surface out to the edge of the occulting disk that we can't see. And that's why observing the sun during an eclipse is important, because this area is not observable with our current technology. That's changing a lot soon. But with our current technology, we can't see the changes that are happening in the solar atmosphere if some kind of an eruptive event occurs. So this eruptive event was a particularly large one. It caused a coronal mass ejection, which is a huge cloud of charged particles, protons and neutrons and others, that blast off from the sun and arrive at Earth, and then they can cause effects of loss of GPS. There are other effects on satellites in orbit, and we'll go into some of the other effects there. But let's go on to this. Is a artist's rendition of a coronal mass ejection beginning at the sun, moving through space, and then interacting with Earth's magnetic field, which you will see in a moment. So the cloud presses in on the magnetic field, causes the field line to flip backwards, and then there are things called reconnection events or annihilation events of the magnetic field that then cause particles to move closer into the Earth, and aurora get much more intense, and there are radiation effects close to the Earth and in orbit around the Earth. So astronauts on the ISS have to be very careful at this time, and airline pilots have to actually change their flight path so that their altitude is lower, so that they're not affected by the radiation that has been beefed up by this coronal mass ejection from the sun. So all of this is called space weather. And we're concerned about space weather because we have so much more technology that we're using today that is or could be affected by the conditions that the sun creates in Earth's magnetic field. Now, I don't want you to think that this is all a bad thing, because when the sun produces a lot of sunspots and a lot of solar activity, its magnetic field is also beefed up so that we are more protected by galactic cosmic rays. And that's a good thing. But then there are these other events that can happen, and that they would affect humans in space. They could affect satellite operations. And even on the ground, they could affect power and communications. So the power lines, there was actually an event that happened in 1989 that affected a transformer in New York, I believe, and caused power blackout in Quebec. And this kind of transformer is huge and costs $1 million, and they don't make them every day. They only make them when they need them. So, you know, they take a while to put together too. So can you imagine being without power for months or maybe longer? That could happen with a large space weather event. There has been some discussion of climate change due to some of the solar activity, but there's not a lot of actual climate change that occurs due to space weather. There is some interaction, but mostly it's the humans that are changing the climate. So we want to be able to predict these solar cycles. And so there are these theoretical ways of doing these predictions that Dave Hathaway has used. And this plot actually shows the number of sunspots plotted on the y-axis versus time on the x-axis. And that's the jagged line. So everywhere you see the jagged line, those are sunspot numbers that are being plotted on this diagram. And the other part is Hathaway's prediction. The solid line is his prediction, and this is the error on his prediction with the dotted line. So plus and minus is his error. So notice here that just before 2010, just before the Solar Dynamics Observatory was launched, we were in a very low, deep, long solar minimum. And so what do we expect this solar minimum to be like? That's the question. And so these types of predictions that he has used can help us better understand and predict what the sun is going to do. So here we have 2010 compared to 2013. So you see that the sunspot number went up quite a bit. And Hathaway's predictions get better once the cycle has started. So his prediction narrowed in on what the cycle was going to do. And basically the prediction for now is that we will have another low, that is low sunspot number for this minimum, and that it may be fairly long. So we have used observations of telescopes along with mathematics and mathematical tools. We now have satellites in orbit that can look at the sun 24 hours a day, 7 days a week. And we've begun to understand a whole lot more about our star, the sun. We're making great progress in understanding the cause and being able to predict the solar cycle. Cycle 24 peaked in April 2014, and then the minimum was December 2019. So that means the new cycle is starting, but it's starting kind of slowly. Solar cycle 24 was the smallest one in about 100 years. So I will stop there. Probably talk too long. And ask if anyone has questions. I would like to also say that if you want to look at the sun every single day, no matter what the weather, there's a website called solarmonitor.org, and I should type that in the chat, which I will do once I stop talking. But solarmonitor.org will show you the sun in a lot of different colors of light, and you can see the sunspots, you can see the chromosphere, you can see the corona. And you can also go to the SOHO site to see some of these coronal mass ejections.
I'll add on to that. I typed in the chat a few minutes back that I've got this app on my smartphone called the Sun Now, and it probably draws the data from your source you mentioned, Mitzi, but you can look, in real time what the last image of the sun was in both hydrogen alpha and white light. So it's pretty cool to see if any sunspots today or flares going on, and you can kind of like watch it over time and see how the flares are changing. So it's pretty cool.
Another website that I've used is spaceweather.com.
Yeah.
That's a good one too.
That was done by Tony Phillips, who has worked with us in the past, and he does put out a lot of really good stuff. So spaceweather.com is another really good site to use.
All right, I'm going to go ahead and stop the recording. Okay, we'll stop. I think.
All right, well, thank you very much, Mitzi. Great presentation.
You're welcome, thanks.
All right, we're going to transition over to a recorded presentation from Jeff Delmas that he's been teaching in his observational astronomy course. This one is about sky coordinates and sky maps. So I am going to mute myself and bring that up on the screen.
Once again, tonight we're going to be going over sky coordinates, and that's really the basis for understanding where things are in the sky and how to look them up. Without understanding sky coordinates, you're really going to be limited to things that you can see and learn on your own with very little additional information. And the second half of the session will be on telescope and mount designs. So we did a little bit of that last week, but today we'll go a little further in depth. And then next week, observing progression, how to kind of build on success, starting with things that are easy and moving to things that are harder, and how to know what things are easy or hard. Let me get some housekeeping things over here. And Jared, if you could monitor the chat, if anyone has any questions, go ahead and submit those in the chat tool, and Jared will curate them and interrupt me when appropriate. And I'll stop from time to time and ask if there are any questions. So finding objects is really perhaps the hardest part of amateur astronomy. Now you can get a lot of help from modern computerized telescope mounts, but they're really no substitute for actually knowing the sky yourself. I kind of equate it to going into a new city and using GPS. And GPS is great, it'll help you out, but it's hard to know one thing relative to another or in relation to another unless you really learn the city yourself by living there. This is the best way. And living under the sky, which you do all the time, you can learn it as well as any city. I mentioned this last week. Most people think, if they think about it at all, that it takes a year or so to see the entirety of the celestial sphere, but that's not true. You can actually see all but a very narrow wedge of the sky if you stay up all night. Now, I know this is not something that you're going to all rush out and do, but I do recommend that perhaps 1 or 2 nights a year, you take the time to do this very thing. It really makes the sky look much smaller and more knowable than going out every few weeks and looking to see what's up right now. Learning the patterns of stars in the night skies, it's very rewarding on its own. I just enjoy looking, and some people have a real knack for it. Others, like me, struggle for years, and honestly, if I were to have to write down the zodiac in order, I would probably fail that test. In the end, it's just a map, just like any other map, map of a city or map of the world. And here's how we do it. So I will say there was a good reason for the Ptolemaic system that I mentioned last year. It lasted for 1,200 years, perhaps really longer than that, but before the Copernican revolution. But the basic concept that the stars are stuck to a sphere and the Earth is at the center of that sphere is a useful concept. And that is the form of map that we use to this day. We know that the axis of the Earth is tilted 23.5 degrees relative to the plane of our orbit around the sun. And if we take the equator and project that line out into the heavens, we form a plane. And if we project that onto the celestial sphere, it forms a great circle called the celestial equator. But the sun, moon, and planets all move around this other line or this other plane. That great circle is called the ecliptic, and it's tilted 23.5 degrees from the celestial equator. Now, because it's tilted, because our axis is tilted, and these two planes are not parallel, they intersect at 2 points. And the 2 points they intersect at are called the vernal and autumnal equinoxes. And you're all familiar with that. You know that the end of summer just occurred at the autumnal equinox, and that winter will start at the winter solstice, and spring will start at the vernal equinox. Vernal literally means spring in Latin. Now on the sphere, we use a coordinate system, and there are 2 ordinates, and the names are kind of weird. The names of the ordinates are right ascension and declination. Right ascension is measured from the vernal equinox, and you see the symbol here is for Aries, because Aries is where the celestial coordinate system, well, that is where the vernal equinox existed when the coordinate system was established. In reality, the vernal equinox has moved, and I believe it's in Pisces. Doug, you may recall. And if you think, for example, that your sun sign, that you were born, for example, in May, you're a Taurus. Well, actually, you're an Aries. Yeah.
Is this the current vernal equinox? This point here?
Well,
that next to the gamma?
Yeah, well, this is the symbol for Aries.
Yeah, and then this would be the symbol for Pisces, since Pisces is right next to Aries.
Yeah.
If you had the symbol for it.
Right. Yeah, the point is the Earth's axis actually wobbles, which is called precession, and it takes 24,000 years. So 2,000 years ago, we're 1/12 of the way through the precessional circle, and 1/12 is exactly a month. So we're actually a month behind where the coordinate system was established. But that's sort of beside the point. I probably shouldn't have brought that up. But, okay, so right ascension is measured in time units, hours, minutes, and seconds. But it is considered an angle. And 1 hour, and that angle is related to the Earth's motion, 24 hours. So it's 360 degrees divided by 24, or 15 degrees. Now that's true only on the ecliptic, that it's actually 15 degrees, because up here, of course, at the celestial pole, it's 0 degrees, but it's just a matter of the cosine of your declination of your height here, how many degrees it actually is. But it's convenient for you to think of it as 15 degrees per hour. And another way to think of it is that 1 degree equals 4 minutes of time. This is not minutes of arc. I know this is a little bit confusing, but you have to think of right ascension in terms of time, not degrees, minutes, and seconds of arc. And then we have declination. And declination, so right ascension is this dimension, kind of equivalent to your longitude, really. And then declination is equivalent to your latitude, is the up and down motion. And its name makes a little more sense, how much of a decline or ascent you have. Now, it is measured in degrees, minutes, and seconds of arc. So those declination units are always the same, as opposed to the time units translating. The time units translate to degrees differently depending on the declination, but you really don't need to know that. I mean, you don't need to use that. It's immaterial, really. So the key is that right ascension is measured in time units. Declination is measured in traditional angle units of degrees, minutes, and seconds of arc. So for example, here is the coordinate for this star right here. It is 1 hour and 34 minutes and 20 seconds RA, and then declination is plus 47 degrees, 36 minutes and 14 seconds. Now, when you're standing on the Earth, you can't see the entire celestial sphere. You have a horizon. And there are some key things that are local to wherever you are on Earth. It's just part of your local coordinate system, if you will. So the Earth behaves like a giant clock. We know that we complete one circle every 24 hours. Now, technically, there is a difference between solar time and what is called sidereal time, and that difference is 4 minutes because it takes a little bit longer. The Earth in one day has moved slightly around the sun, 1/365th of its journey around the sun. So in order to come back and look directly back at the sun, where the sun will be exactly overhead once again, we have to go a little bit further than if we turn around and look at a specific star. So a solar day is 4 minutes longer than a sidereal day, but you don't really need to know that. They're close enough to where you just think about it as 24 hours. So right ascension, it's a funny name, and it gets its name from the fact that if you face north, then everything that comes into view, the sun, the moon, the stars, everything rises in the east, which is to your right. So things ascend on the right as you're facing north. So the hour angle that is at your local meridian, and the meridian is the line that connects north to south, projected up into the celestial sphere. So in other words, it's the line that goes straight overhead. That is called your local meridian. And the hour angle that is at your local meridian at any given moment is the local sidereal time or star time. Sidereal is Greek, I believe, for star. It may be Latin, I don't know. And the angle from the north horizon to Polaris, we're kind of lucky because it just so happens that Polaris happens to be at very close to the North Pole, North Celestial Pole. And that angle is your latitude, and that becomes important later on when we talk about telescope mounts. So here is an image. It's kind of a pictorial image of the entire sky. This is very much, in fact, I think it is a Mercator projection of the sky. And because it's a Mercator projection, the further north or further south you get, the more distorted the images are. So for example, here's the Big Dipper, which looks nothing like this, of course. It's just stretched too far at the north. But at the equatorial region, things look rather normal.
Jeff, that was
Yes.
the Little Dipper, and over here's the Big Dipper.
Oh, you're right. That's Ursa Minor.
and they both look skewed.
Yeah. Here's the Big Dipper. It looks okay, not too bad. Yeah, this is Ursa Minor, the Little Dipper. The Little Bear, too. Okay, so we've got our celestial equator runs right down the middle, actually connecting this point to this point to this point, and then this yellow-green line is the ecliptic. That's the line that the sun and all the planets go through. And you can see the zodiac here. I'm just looking, Aries, Aries is not, oh, here's Aries. So the vernal equinox originally was at Aries, but now is in Pisces. And then here's Taurus, Gemini, Cancer, Leo, Virgo, Libra, Sagittarius, oh, Scorpius, Sagittarius, Capricorn, Aquarius. This is a more common way to look at the type of map, and they are very often portrayed in kind of negative, you know, with a white background and black or other color stars and objects. This happens to be a map of all the Messier objects. Now, this thing that's swooping through here, and it was, I believe, yeah, swooping through here as well, this is the Milky Way. So you see that, it's the Milky Way, and this is the ecliptic. This map actually didn't have the ecliptic in it, so I drew it in myself, which is why it's not perfectly sinusoidal. Now, we're all familiar with constellations, but constellations in astronomy mean something a little bit different than you may be accustomed to. Normally, you think of a constellation as a grouping of stars, but as astronomers, when we refer to a constellation, we are really referring to a specific area of the sky. It is really a complicated shape within which are the stars that typically make up the constellation. And the IAU, the International Astronomical Union, is the governing body charged with naming and mapping the sky and everything in it. They're the same group that demoted Pluto from a planet to a dwarf planet. I happen to think they were right. Even as a young person, I thought, you know, Pluto's a weirdo. Sometimes its orbit is closer to the sun than Neptune. It's not a well-behaved planet. Its orbit is tilted more than any other planet. Why did they ever let it into the club? So the IAU has partitioned the entire sky into 88 constellations. Now that's for both Northern Hemisphere and Southern Hemisphere. We typically don't need to learn the Southern ones, but you're welcome to learn them all if you want. And any point in the sky, RA and DEC, if you call out any coordinate, then that point is in one and only one specific constellation. So mathematically, the sky is a partitioning of the constellations make up a complete partitioning of the sky. And consequently, once the IAU did this, and I should have found out exactly when that was, when they standardized the map. Some of the ancient constellations are no longer recognized. And in fact, we've got, well, I'll show you in a moment. I'm actually going to skip this. I had some trouble with this, and it wasn't very effective anyway, but it kind of shows some common constellations and then takes you around. Based on their distances, constellations may look like a dipper, but when you spin them around or travel around them, they're going to look differently. So here's really a map of the partitioning without the stars. And a couple of things you see, we've got the zodiac highlighted with bold outline. And one thing that you may notice is there are, I think this is the only one, Serpens is, the serpent is divided into two regions, Serpens cauda and Serpens caput. Serpens cauda is the head of the serpent and the tail. And frankly, I'm not sure I'm pointing to the head here. I don't know if the head's here or there. I forget which one's which.
Yeah, this one's the head and this one's the tail.
Well, which one am I on right now?
Serpens caput.
Okay. Always.
This is Serpens caput is the head.
Yeah,
and Serpens
and
cauda.
Technically, Ophiuchus should be one of the members of the zodiac because the sun goes through Ophiuchus just a little bit. I think it actually grazes the corner like right around here. But that's another thing. Then we've also got, in ancient times, there was the Argo, the ship that Jason sailed in. It is now divided into three constellations. Puppis, which is like the poop deck. Vela is the sail, right? Mm-hmm. And Carina is the, that's the body of the ship?
Yeah, the hull of the ship.
The hull, right, the hull. Thank you.
Hey, Jeff.
Now, yeah.
I was going to say the IAU, they formalized the constellations in 1928 and then published it in 1930. So since 1930,
okay,
there have been 88 constellations.
Yeah, thanks for looking that up. Mm-hmm. I'll add that into the slide. In observational astronomy, asterisms are often more useful to us than constellations. Because there are no boundaries in the sky, it's hard to know whether you're in one constellation or another unless you look it up on a map. And it's really the maps that matter when you're dealing with one constellation or another. But asterisms are popularly known patterns or groups of stars that can be seen. And it may appear quite similar to the definition of constellation, but now that you know constellations are really a partitioning of the sky, asterisms are groupings of stars. So it's more of a visually obvious collection, and then the imaginary lines used to mentally connect them. There are no official asterisms. I don't think the IAU addresses them at all. But we know quite a number of them. For example, the Big Dipper is not a constellation, it's an asterism. It is a portion, really only about 1/3 of Ursa Major, the Big Bear. And Cassiopeia, we're familiar with the W of Cassiopeia more than any of the other stars that are part of Cassiopeia. And here's a few more fairly well-known, or one very important asterism, I should say, the Summer Triangle. And it's quite prominent right now. And so I really wanted to feature it. And it is comprised of Vega, which is the brightest star you'll see overhead in the summer. And that's part of the constellation Lyra. And then Deneb, which is the tail of Cygnus, and Altair, that forms the Summer Triangle. This is very large, so it's it's quite a large triangle, but it is rather prominent. Now, one of the key things kind of within the summer triangle is if you look along the line between Vega and Altair, about 40% of the way from Altair is this thing called the coat hanger. And I didn't want to include the technical name for it here. We'll just call it the coat hanger for now, and we'll get into its catalog number later. But it's a wonderful target for binoculars. You can make it out with the naked eye, but it's a little faint, but not, you can find it. It's findable. Here's a couple more. The teapot of Sagittarius. Honestly, I simply equate the teapot with Sagittarius. As far as I'm concerned, that is Sagittarius. Likewise, the Great Square of Pegasus. It's called the Great Square because it is truly large, and Pegasus is one of the largest constellations, if not the largest. I frankly don't know if it is or not.
Jeff, a lot of asterisms are kind of colloquial. They're
correct. Yeah.
They're various. Nations have their own.
Right, different cultures and
different cultures. Like the Big Dipper here in North America, and in like British countries, English, Great Britain, Scotland, and all that, they call it the plow.
Yeah, that's right.
And the Scorpius, the Hawaiians traditionally call it the fishhook.
In South America, Orion is called the alligator or caiman because Orion is flipped upside down. Its feet are up by its head and down by its feet.
Okay, so enough about the equatorial coordinate system. I'm sure you've got it all down by now. So now we're going to flip to another coordinate system, a local coordinate system called the altitude azimuth or Altaz system. So it's really often convenient to orient yourself to your local position on the Earth relative to the sky. And your local coordinates are often used for your telescope orientation. Now, it's not really important that you ever be able to manually transform between Altaz and equatorial coordinates. You can use software to do that typically. I've never really had the need to do that. But many telescopes are built on mounts that use Altaz or Altaz kind of orientations. And this is what it looks like. Now, I referred to your meridian earlier, and your meridian is the circle, really a line, but it looks like the line that goes from due south straight overhead to due north. And straight above you is your zenith. Actually, there's a word for straight below you. It's called nadir, N-A-D-I-R, nadir. But you can't see it, so it's of no use. But your zenith is often useful. And then, of course, your horizon is like this, whereas the Earth's equator projected into the sky, or the celestial equator, is this blue line. Now, the coordinates, when you're referring to something in Altaz coordinate system, your azimuth, or your left-right orientation, is from is 0 at north, and then you sweep around clockwise from that to form an angle. And both ordinates in the Altaz coordinate system are angles like you're familiar with, degrees, minutes, and seconds. The advantage of Altaz coordinate system really is that it is always local to the observer. So no matter where you are, that Altaz coordinate system is relative to you, not relative to the Earth or anything else. And it coincides with the most common type of telescope mount, which is also called Altaz. Now, even when using an equatorial, or perhaps especially when using an equatorial mount, there's often a big difference between looking east and looking west. And that is based on your local meridian. Now, you're not going to find any maps written in Altaz coordinates, because since the Altaz coordinate system is relative to the observer, the map would change everywhere you moved. I mean, not by moving around in a circle or something like that, standing in one spot on the Earth, but as you move from one spot to another on the Earth, and time gets into it as well. And if you really need to transform one to the other, it's easy enough to use software. But like I said, I really have never had to do that. It's more a coordinate system of convenience than it is a coordinate system that you need to know anything about, number-wise. Okay, another important thing that people are always curious about, in fact, I would say this is probably the number-1 question you'll get anytime you share a view through your telescope, and that is, how far away is the object you're looking at? And over time, you will find that you don't personally care that much about how far something away is, because you get kind of numb to the distances. The distances are so phenomenal. But people will ask you, and distances are important in astronomy. It's one of the most important things astronomers try to determine, really. But the objects are usually measured in one of 3 distances. So you're probably most familiar with light time, light years, but it could be light minutes or light hours. This is most commonly used by non-professionals for long distances, for great distances. Now, the speed of light is 30,000 kilometers per second, and that is an easy number to remember. If you try to remember it in miles per second, it's a little bit harder, 186,000. But this number becomes very convenient in a lot of situations. So 1 light year, or the distance that light travels in 1 year, it's just too big to even fathom. 9 times 10 to the 12 kilometers, or 6 times 10 to the 12 miles. That's 6 trillion miles. But here's a nice little trivia, and you can remember this. Light travels about 1 foot in 1 nanosecond. And that's because a foot is about 0.3 meters. And if you divide 3,000 meters, 3,000 meters is 300 million meters by a billion. If you divide 300 million by a billion, you get 0.3, which is about 1 foot. So there's a little trivia that you can keep around and use at your next dinner party. Now, the second type of distance unit is the parsec. And really the that is the most commonly used distance for professionals dealing with stellar distances. And it's about 31 trillion kilometers. It's about 3¼ light years. And that's how I always remember the relationship really is 3¼ light years, or roughly, let's see, you know, I can go if I go 3 times that, I'll get 10. So 10 light years is roughly 3 parsecs. Is another way to remember it. And then the third type of unit is the astronomical unit, which is the distance from the Earth to the Sun. Now, 1 AU is pretty big. It's 93 million miles. But in terms of dealing with stars and nebula and galaxies, it's puny. It's way too small. So these units, astronomical units, are only good within the solar system. So the distance to the nearest star is about 4¼ light years. I'm not going to get into a fight over which star is the nearest, but let's just assume it's 4¼ light years away, and that's about 270,000 astronomical units. So even the closest star is over 250,000 astronomical units away. So every other star is typically millions of astronomical units. And here's what a parsec is. So how did they come up with the parsec? It's the distance from the sun at which the radius of the Earth, the radius of Earth's orbit, subtends an angle of 1 second of arc. So a star put out way out here has to be far enough away that this angle is 1/3600th of a degree. And it comes out to, like I said, about 3¼ light years. I do have a movie that I think is very good, and I will show that. And I think I set everything up. Give me a thumbs up if you can hear the sound.
All right, that concludes the first section that Jeff's on the sky coordinates. Jeff is online. Anybody have any questions before we launch into his topic on telescopes?
Eric, did you want me to start recording this?
Yeah, you can start the recording.
All right.
I've got mine
I didn't record just because I think that's already video.
I've got mine going as well. So, all right, I'm going to launch.
Okay, well, I'll
pause it. Let's see. Share. Move back.
Okay, well, I'll go ahead and get started. I think just about everybody's back.
Jeff, I did some checking, and Hydra is actually the largest.
Oh, yeah. Mm-hmm.
Covers 3% of the celestial sphere.
And it just goes around a large area. It doesn't seem that large. Pegasus certainly is impressive. I mean, it seems very big.
It's definitely big, especially because you see it overhead.
Mm-hmm.
But after Hydra, it's Virgo, and then Ursa Major.
Oh wow!
Cetus and Hercules.
Okay, so let's get into telescope designs and key elements of those designs. We'll talk about the terms and measurements of telescopes, the various types of telescopes, and then about a little bit about what you can see through your scope and how to go about learning to use your scope. So this is the same slide we had last week. This is the Galilean refracting telescope design, and all refractors are some variation of this. The big difference between one refractor and another is the complexity of the objective lens. But other than that, it's just a long tube with a lens on one end and an eyepiece on the other. And the focal length is the distance from the objective to the focal plane. And your eyepiece, one thing that I really like to do when the class is live and we can go outside afterwards is that you can take a piece of paper, you can take a small piece of paper and preferably something that you can mostly see through, so like a piece of wax paper or something, and then push your focuser all the way in so it's as low as possible, take the eyepiece out, and then put the piece of paper over the tube where the eyepiece goes and move it up and down, and you will see the image formed on that piece of paper. So the way a telescope works is the image, it's all a telescope is a light amplification device. So it takes in a large amount of light and concentrates it onto a small space. And that simply brightens the image. And then you use an eyepiece, just like a magnifying glass, just like you would look at a coin or a stamp or something like that with a magnifying glass, but you're magnifying that image that's floating in space, in the air, on that focal plane. And that's all any telescope is, whether it's a lens type or a mirror type. So aperture is the diameter of the lens, and I've got down here, aperture is the king of telescope measurements, because that tells you how much light you're gathering. In fact, there are large amateur reflecting telescopes are often called affectionately light buckets because they collect light. And of course, this is the Newtonian. It's got a mirror, and the mirror surface is on the front, not on the back, like the mirror in your bathroom is reflective on the back. So you can't use just any mirror. And then there's compound telescopes or catadioptric telescopes, which combine both lenses and mirrors to form an image in a typically more compact design. In fact, this is one right here. If you look at my video feed, I'm going to take the front of it off, front cap, and as I turn it around, you can see it's got a lens on the front, but it also has two mirrors, and one of the mirrors is glued to the lens on the front. And this is actually very much like this diagram, and the secondary mirror has somewhat of a telephoto effect. So even though this telescope is very short, the focal length on it is 1¼ meters. So the focal length is 1,250 millimeters, which is, you know, wider than I can really show you. So it's longer than this one over here, which is about 900 millimeters focal length. Okay, so we've got refractors, we got reflectors, we have catadioptrics. Why should I pick one or another? What is good? What's bad? And I do want to preface this. I am not trying, there is a good purpose for every telescope. So this, for example, is a little 3-inch Newtonian with a 900 millimeter focal length. This thing altogether weighs about 9 pounds. So it's highly portable, and it's good at looking at planets. It's good at looking at some bright nebula and star clusters. So I'll just kind of go through the advantages and disadvantages of different types and then help you understand why some machines are better for viewing some types of objects than others. Refractors tend to have the clearest, sharpest views. And that's mainly because you see we've got a secondary mirror on the mirror types, and there's a lot of alignment issues that you get with mirror types. And I mentioned in the last session that refractors tend to have color aberration, or what's called chromatic aberration, and that's only true of simple refractors of the type that existed from the time Galileo started it until the 1800s, roughly. Modern achromatic lens systems minimize that chromatic aberration. And another great thing about refractors is that they are factory aligned, and you never need to realign them. In fact, if you attempt to realign some yourself, quite often the lenses, not only do they have to be aligned like this, but they have to be aligned axially as well. So you should never really attempt to realign a refractor unless you contact the manufacturer to find out. And I have done that before. I've contacted the manufacturer to find out about cleaning a complex lens and potentially realigning it and things like that. Now, the disadvantages of refractors, the main disadvantage is the cost. Because of the number of critical optical surfaces, a mirror has one optical surface. It's a mirror. You can't look through it. So there's only one surface to get right. But a lens has two optical surfaces, and they have to be constructed relative to each other perfectly. And not only that, but to have an achromatic lens, it's really a system of lenses. It's not just one piece of glass. It's multiple pieces of glass, often made of different materials. And so those things, to manufacture them is very expensive. And sometimes, like if you were to get a Takahashi, say, which is a Japanese brand of telescope, that in particular, Takahashi refractors are extremely expensive, but all Takahashis are very high quality. And another disadvantage is that you're limited to about 6 inches of aperture unless you have extremely deep pockets. And if you recall from last week, the largest lens ever constructed, I believe, was like, oh gosh, I can't remember. It was like the Paris World's Fair or something like that. But now I can't remember. I think it was like 60 or 70 inches, but it doesn't even, it's not in operation anymore. But the 40-inch Yerkes Observatory in Wisconsin, that is working. And that, I believe, is the largest one in the United States. So 40 inch is the largest one in the United States. So reflectors, so you can kind of think of the advantages and disadvantages of the refractors, kind of flip them over, and those are the disadvantages and advantages of reflectors. So the big advantage is that it's the lowest cost for any given aperture. And since aperture is king, reflectors dominate the world of amateur astronomy. You know, that used to be utterly true. I mean, that was extremely true in the 80s, 90s, even the early 2000s. But with modern astrophotography systems that are far more sensitive than your eye, refractors have made a huge comeback because of the clear, sharp views they produce. So reflectors eliminate chromatic aberration, so you don't have to worry about that. And that's why they are cheaper. They tend to be much lighter weight for any given aperture. Like I said, this 3-inch reflector, the whole thing, including the mount, weighs 9 pounds. A 3-inch refractor is going to weigh, I don't know, somewhere between 12 and 20 pounds for the tube, and then the mount that you get for it. So it's not a lot more, but it'll be more. And some designs, like this mirror design, are very compact for any given aperture. Now, the disadvantages are, of course, the central obstruction blocks some of the light, but that it's very small relative to the, I mean, you just do the math. You typically block somewhere between 5 and 15% of the light. And then reflectors have what are called spider vanes. I don't know if you can see this. Not much. This reflector is kind of small, but the secondary mirror is held up by a spider. Now that's not true on this one because the secondary mirror is glued to the front of the lens. I'm glued to the back of the lens on the front of the telescope. But all of the reflectors require alignment, and you may be able to see all the little screws and knobs and things on the back here of this telescope to do that. You don't have to do that often, although I know some people who do it every time they go out, especially with catadioptrics. Now, let's talk about catadioptrics, the combination, which is what this guy is here. They are lower cost for a given aperture than refractors, but usually more expensive than simpler Newtonians. And they have the same advantages of Newtonians, you know, no chromatic aberration and that kind of thing. But their compact physical size makes them much easier to move around. And in fact, when I travel, I will usually take this telescope here. And because of that convenient lens on the front, you can glue the secondary to the front lens, and you don't have to have a spider. Spiders produce those diffraction spikes, those star-like spikes that come off of stars in photos. Some people actually like them in their photos. A lot of astrophotography you'll find is art more than science. And that's great. You're taking pictures of beautiful targets. They are a little easier to collimate than Newtonian catadioptrics. Not this one, actually, but others. Now, aperture, remember I said aperture is the single most important factor in choosing a telescope. You really want to go fairly large with your aperture. You know, you tend to, I would recommend, if you only had one scope, you would want to go a little bit bigger than you might think you want to go. And I don't love this comparison here because it kind of gives you the impression that the larger the mirror, the larger the magnification you get, and that's not true. The magnification comes from the eyepiece you use, really. What is true, though, is that the larger the aperture, the sharper the image will be, and the more that you can magnify it. So here with a 5-inch aperture, you see, I can't see the Cassini division, the split in the rings, but up here at 8 inches, I can see it, but it's not real distinct. But here at 14-inch, I can really tell the outer bands from the inner bands, and that Cassini division, this dark ring here, is extremely prominent. And remember what I said before, that the only purpose of a telescope is to gather a large amount of light and concentrate it to a small image. Magnification is the focal length of your main objective or mirror divided by the focal length of the eyepiece. So, for example, if I have a 50 millimeter eyepiece on a Celestron C8 that has a roughly 2000 millimeter focal length, then I get about 41 power. And that's a typical kind of power that you would use. Yeah, so there's a question, is it normal for most Newtonians to flip your view upside down? Absolutely. Upside down, possibly backwards at the same time. And why do most experts tell us that you need to leave your scope out to adjust to the temperature? It's for two reasons. One is there are currents that get set up within the tube itself that can interfere with the quality of the image. And the other is that things may be aligned, but they may have different thermal properties and come to the same temperature at different rates. So the mirror glass takes longer to come to thermal equilibrium than metal. So yeah, it's advisable to leave your telescope out for 20, 30 minutes before you do any kind of serious viewing. But I never let that slow me down. I set things up and start viewing right away. My viewing typically, the image will typically get better as it reaches thermal equilibrium. So one of the key things here is that magnification is one of the least important attributes of your telescope. In fact, it's theoretically possible to push your telescope to virtually any magnification. But as a rule of thumb, so there's two types of optics. There's theoretical optics and there's physical optics. Theoretical optics says, oh, if I want 1,000,000 power, all I need is a lens with a 0.0001 focal length. I'll go make one of those. But there are physical limits to optics, and you will never reach it. Of course, your view would be horrid. And as a rule of thumb, the maximum usable power is about 50 times the aperture of the telescope in inches. Powers higher than that give you dim, fuzzy, low contrast views. And you really have to remember what you're doing. Remember I told you about the technique of putting a piece of paper where your eyepiece goes. So that piece of paper will show the image floating in space. Now, it doesn't matter what eyepiece you use, you will never make that image brighter or bigger or anything. That image is what it is, because that's the main mirror or the objective lens that's forming that. All you're doing with a shorter focal length eyepiece is looking at a smaller and smaller and smaller piece of that image that's formed. And so you can see that the smaller area of that image that you're looking at will be magnified higher because you're looking at it, as at a smaller piece, but you're looking at less light. So it will be dimmer and dimmer and dimmer the higher the magnification goes. Higher powers are mainly used for lunar, planetary, and binary star observations. So these are all targets that have a rather high inherent brightness and, except for the moon, have very small inherent angular size. So binary stars, they look like pinpoints, but you can magnify them quite a bit because their image is not spread over an area. Similar with planets. And for the moon, you use high magnification because it is inherently very, very bright. And frankly, dimming down the moon is your problem. You may want a lunar polarized filter to observe the moon. So don't believe manufacturers who advertise a 300 or 750 power telescope, which is only 60 or 80 millimeters in aperture. That is, at the very least, it's misleading. And you'll find out that no matter how large the aperture is, most of your observing is going to be done at relatively low powers, 20 to 50 power. With lower power, the images will be much brighter and crisper and provide more enjoyment and satisfaction with the wider field of view that you get. Okay, now on to telescope mounts. Another kind of rule of thumb, and I don't even have it here, is that the mount should cost about the same as the optics. In other words, spend a good amount of money on the mount. And I did that with this telescope because I spent about $20 on the telescope itself and about 20 bucks on the mount. And this one has a mount made for it. And you can, I don't know if you can see much of it. I'll just kind of lift the tripod. It's much more substantial. Okay, I'll go over, there are two general types of mounts and many subtypes within that. So the most common and least expensive are the Altaz mounts. And Dobsonian is the most popular type of that. And that's what this one is here. these mounts tend to be very stable, rather low cost, and support rather large telescopes. So with this type of mount, you can spend more on the optics than the mount and get a very good stable mount. So stability and ease of moving around is really important. And this is a fork mount on this one. And then this is an equatorial mount, a type that's called a German equatorial mount, but because it's got the counterweights. I guess it was designed initially in Germany, but I don't even know who designed it. Now, I did want to show you or demonstrate with this telescope, it actually can be modified. So it operates, I think we can all see this. Let me move it. So it operates as an Altaz. Now, the thing about an equatorial, I'll go into it in detail, is that this axis is aimed parallel to the Earth's axis, and that gives us some advantage when finding things. It aligns the telescope with the equatorial coordinate system. That's the main thing it does, but it makes it easier to track things, and it makes it easier to do long exposure photography. In fact, I would say that it enables long exposure photography. So this mount here is an Altaz mount, but I can flip this little thing and tilt it over, and then it becomes an equatorial mount, and it's got readings on this bar that I can set my latitude, and I have to actually go quite far because we are pretty far south. And then this would be aimed at the North Star along this axis here. I'm going to put it back down. I rarely use it in the equatorial thing because I really don't need to unless I'm doing photography. Okay, so let's talk about advantages and disadvantages of Altaz. The main advantage is simplicity. It's just the least expensive, simplest type of mount. And they tend to be very stable. In fact, this kind of demonstrates it. When I convert this to an equatorial, it's less stable because it's kind of off balance a little bit, which is why I tend to use it in the Altaz. If I'm doing visual observations, I use Altaz. They're very easy to set up, and they're really the best option for new observers, whatever the age. Now, the disadvantages come when you're trying to track things, and even when you're visually observing, you have to move in both axes to track anything, to keep up with whatever you're looking at. And you can't really use it for long exposure photography, but a lot of modern photography, and I think Session 6, I believe, is on astrophotography. We'll go into it in detail, but a lot of modern photography is done with video where you're taking many, many, many images, and you can align those in software. So it's not so much of an issue as it used to be, but any long exposure, most video camera work is done for planetary and lunar photography. Okay, so why would you want to use an equatorial mount? Well, one of the main reasons, as I mentioned, is alignment with the equatorial coordinate system. But the big advantage is that it requires only motion in one axis to track targets. Because you're aligned with Earth's axis, all you need to do is move the telescope in the opposite direction of the Earth. So the Earth is diving to the east. The Earth moves around to the east. Where you're standing, you're going to be east of where you are in an hour or in a minute. And so what you do is you rotate the telescope in the opposite direction to the west, and that keeps you tracking a specific star or any other celestial object. Now, field rotation is when you look in the eyepiece and whatever you're looking at starts rotating like this. And that occurs over a long period of time. And that's why it's not, that's why the Altaz system is not good for long-term exposure. Now, obviously, the disadvantage is going to be in the area of cost. They tend to be higher cost because of their complexity, and they're heavier if you especially have a German equatorial with counterweights. So this is just a extra mass you're carrying around for no good reason other than to balance the telescope. Fork mounts don't have counterweights, so they don't have that particular disadvantage. And then another thing, it takes longer to set up. You have to, in order to get the advantages of an equatorial mount, you have to align it with the Earth's axis. And you have to do that every time you go out unless it's a permanently mounted telescope. I don't have a permanently mounted telescope. Now, a lot of telescopes come with computerized mounts, and there are two general forms that I want to talk about. The first is called digital setting circles, and there are some brand names, but that's the generic name. And the second is called a go-to mount, where you tell the computer, I want to go look at Jupiter, and it'll move the telescope. And that's what go-to means. So digital setting circles, traditional setting circles, in fact, there are setting circles on this right here and up here. You can't really see them, but once you get your telescope aligned and you figure out what your local sidereal time is, then you align your setting circle with local sidereal time, and you look in a reference for the object you want, and then you move your telescope until the setting circles line up with the object that you looked up, its coordinates. And then, lo and behold, you look in the eyepiece and there's your target. Well, digital setting circles basically take the work of all the aligning and determining your sidereal time and all that stuff away from you. And all you have to do is point it at two stars, two known stars, and the computer figures everything out. And so digital setting circles, there's an encoder in each axis that tells the computer where the scope is pointed. And the way these work, yeah, sometimes these are called push-to systems. And I like that term, really, because you're the motor. All you have to do is align on two stars. And I've got a push-to system, and I really love it. It's so easy to use. I don't have to worry about power. It doesn't have motors, so I don't have to plug it in. I can take it wherever I want to go. It runs off a 9-volt battery, I think. And in fact, it is this very, this is my push-to telescope here. And you see the keypad, I can key in things. And once I set it up, it's amazingly accurate. I've been real pleased with it. Now, go-to mounts have motors built in to the mount. And they also have the digital setting circles. So they combine the digital setting circles with motors to aim the telescope where you want it to go. And it requires aligning to 2 or 3 known stars during setup, and depending on the type of accuracy you're looking for. Since it's pushing the scope around, it needs a little bit more accuracy, but really not much more than. I also have a go-to mount, and I can put several different scopes on it. And I find that a 2-star mount is usually accurate enough, even for photography that I do. So it still requires polar alignment for equatorial mounts. So you can't just set it anywhere you want and then point it at 2 stars. Now, the push-to that I have, it is an Altaz mount. So all I have to do, I can set it up. It doesn't matter where, what orientation. I just plop it on the ground and point it at 2 stars, and I'm ready to go. The equatorial mount, the first step is aligning this axis, and there is actually a small telescope through the center of this thing that you get down on the ground and look through to see Polaris, to line it up with the North Star. So you got to do that, even though it's a computerized mount. And then once you do that, once you get it aligned, then you have to point it at 2 known stars. So these are both more expensive and they're harder to set up. And I have seen people who get these, you know, and if you're one of them, you don't have to raise your hand. But I've seen people who've never used a telescope before. They buy a nice fancy telescope, and you know, I can't say that's a bad thing to do, because why waste your money on a lower cost telescope if you're only going to eventually buy a better one? Just go ahead and buy the good one. But then they start trying to use it at its maximum capability, at the most automated way. And I've seen people spend 2 hours or more trying to set their scopes up, trying to get it aligned, trying to get a good reading on 2 stars or 3 stars, not really knowing exactly what the theory is behind it, just wanting to look at something. And meanwhile, others who have much lower cost telescopes have set their scopes up and looked at 12 objects. So the goal is to observe, not to run a computer. For that reason, I really don't recommend these for new observers, and especially if you're on a budget. I mean, if you've got unlimited funds, I would say go ahead and get the scope that you think you would want in 5 or 10 years if you're serious about it. So here's my recommendation. Everybody asks me, what do you recommend? I mean, I think we all get that. I know Jared gets that. Doug gets that. What do I recommend? Well, I recommend you get 5 telescopes, because until you have 5, you're not going to have everything you need, because there is no one perfect telescope. But here's what I do recommend. I recommend an 8-inch Newtonian on a Dobsonian mount. Now, you can get that with or without the digital setting circles, because they don't add that much cost. And they add a fair amount, but not a tremendous amount. It's a good compromise. 8 inches is a good compromise between large and small. Once you get a scope that's bigger than 8 inches, it's hard to carry it around. I mean, and you may even realize after you get a 12-inch telescope, I need a different car or vehicle to move this thing around in. So the telescope that you spent $2,500 on winds up causing you to spend $35,000 on a new vehicle to carry it. An 8-inch, the cost will be far less than an equal-sized refractor by far. You can't really get a good amateur 8-inch refractor. So if you do want to go the refractor route, I would recommend somewhere around the 100 to 120 millimeter diameter. That is roughly 3.5 to 5 inches or so. But those can be very expensive. Dobsonian mounts are very stable, inexpensive, super easy to set up. It typically has two pieces, this tube here, and the mount is one piece. So there's not a lot to set up. Equatorial mounts often have the tripod, the mount, the head, then you've got counterweights you got to deal with, you've got the scope, the tube itself. So usually equatorial mounts have, yeah, you can leave some things set up together, but you're typically talking 3 to 5 or more parts to assemble when you arrive at your observing site. And an 8-inch will perform for a lifetime. I mean, it would be something that is better than almost every observer of the 18th century. I mean, actually, it would be better than pretty much every observer of the 18th century because their manufacturing techniques were so bad. And the cost is around $400 for a basic, simple Newtonian telescope on a Dobsonian mount, or about $650 for a push-to. So the push-to adds considerable cost, but much less than an equatorial mount would. I love this by Sir Patrick Moore. I don't know if you all know, he ran the actually longest running television show in England called The Sky at Night, I believe is the name of the show. And he said, telescopes are either good or cheap, but not both. Okay, we'll take a quick look at accessories. How's my time? I'm gonna go a little bit over, but we won't spend too much time on this. We'll take a quick look at eyepieces, finder scope, green laser. Well, actually, I'm going to get into planispheres, star charts, and other things later. But today I'll talk a little bit. But these are other types of accessories that you may want. Most eyepieces are made of multiple lenses, and they magnify the image. Here is a typical eyepiece. This is, oh, actually, I want to show this one. This is my favorite eyepiece. It's a Televue Nagler 13 millimeter. I find that the 13 millimeter is great for all types of telescopes. I typically start out with a longer focal length. This is also a favorite. It came with a different telescope than this. It's a Meade brand, Super Plössl 26 millimeter, but the 26 millimeter Plössl by any manufacturer around that focal length is a very good option, especially when you're when you first set up, remember, use a long focal length eyepiece. Here is a 55 millimeter 2-inch diameter Plössl. Plössl is, let's see, this design here. It's actually, I know it's over 100 years old. I don't remember when it was designed. It's a German name. I kind of highlighted the ones that I recommend. I have an Erfel that for many years when I was younger was my favorite. It's a 20 millimeter Erfel. It's also a fairly wide field of view with very nice eye relief. That's one of the things about Erfel design is very nice eye relief. But all of these are very good designs. And there are other, there are so many good designs out now that it's hard to keep up. But they tend to be expensive. This Teleview 13 millimeter. Okay, so I mentioned that Meade Super Plössl 26 millimeter, it came with a telescope. I don't even remember which scope I got it with, but I believe you can buy them for around 50 bucks. The Teleview 13 millimeter Nagler, it cost me over $200, and that was well over 20 years ago. I don't even know what they cost now. I find when I'm observing that I like to have 2, maybe 3 eyepieces with me. And I usually start out with like the 26 millimeter. So I have a 25 to 40 millimeter for low power. I use this large one on a very long focal length telescope that I have. So at 55 millimeters, I get a fairly low power. And then have a 12 to 15 millimeter. That's this, like this 13. And finally a 5 to 9. Now here's a 5 millimeter Nagler. Also a rather expensive thing. You can get Plössls in all of these, and they are, I love Plössls. They're a great compromise between wide field of view and good eye relief and relatively low cost. Okay, I will say a little bit about a Barlow lens. So a Barlow lens, you'll usually get one with any telescope you buy. Honestly, I don't know why they do it other than they're being cheap, because a Barlow lens multiplies the power of any other lens, but it adds an additional optical element and it reduces your field of view. So to me, it's just not worth. I have a couple of Barlows, and you know where they sit. They occupy space in my eyepiece box, and they are buddies. The 2 of them are buddies, and they never talk to anybody else. Because if I want to multiply the power of my eyepiece, I just get a smaller focal length eyepiece. So Barlows are okay if that's all you have, but the fact that they reduce your field of view really, to me, is one bad thing. But any optical element, whether it's a filter, an eyepiece, whatever that is, any optical element you introduce is going to reduce the amount of light, or it's going to scatter light. And everything you want to minimize that in general. So that's something I always keep in mind. But Barlows do have purpose every now and then. Like if you have a camera, it's a way to increase the effective focal length of your system, or increase the magnification of your camera, because cameras aren't like visual. They are what they are. They're one size with one telescope, but we'll get into that later. So with a camera, Barlow could be quite useful.
You forgot double stars, Jeff.
Yeah,
Follows are good for double stars.
that's a good point because double stars, they are the same brightness regardless of magnification. Okay, every eyepiece is rated with an apparent field of view, and they typically will show them on the eyepiece. And now I'm picking this up and not seeing it. Some of them do, some of them don't. But it's expressed as an angle. Most plausibles have an apparent field of view of 50 degrees. So if you go higher than that, like Nebulars, I believe, are around 70 degrees, they tend to cost more for a higher apparent field of view. But they do pay off. Your true field of view is the apparent field of view divided by the magnification. If your scope is 1200 millimeter and you're using a 25 millimeter plausible with an apparent field of view of 50 degrees, then your magnification is 48 and your true field of view is about 1 degree. So that's pretty good. If you use a 10 millimeter eyepiece with 50 degree apparent field of view, you're only getting a 25 minutes, which is a little less than a half a degree, 0.42 degree. So keep in mind, higher magnification equals smaller field of view. Higher apparent field of view equals wider true field of view. And finder scopes. So even at low power, your telescope's field of view is about 1 degree. We just saw that in this, which is a fairly typical kind of thing. But the area of the sky is over 41,000 square degrees, and 1 degree in diameter is an area of less than 1 square degree. So you could only see a 50,000th of the sky looking through your telescope. So it's like looking through a drinking straw and not being able to see anything else other than what's in the what's through the drinking straw. So you need something to help you see a larger neighborhood. And there are 3 general types: the finder telescope, the heads-up display system, or you can use a laser pointer. I recently used a laser pointer as a finder. Now these are typical finder scopes, and they will usually see about 4 to 5 degrees of sky, which is much larger than the area of the sky that your main telescope can see. So the images produced are likely to be upside down, backwards, both, and often they don't produce the same image that you see through your telescope. So that's kind of a problem. Some, like this one here, has a lighted crosshair, a reticle, to aid in centering the target in the finder. And those are really nice. I like those. And nearly all telescopes come equipped with some. Some have a prism called an erecting prism that corrects this upside down and backwards kind of view. Now, reflex finders, I mentioned this last week. Telrad is the original and, in my opinion, still the preferred. It's a system, it's like a heads-up display system if you've ever seen one of those in a car, or if you're lucky enough to fly jets. It projects a dot or a series of rings onto the sky to form a 1x, one magnification. That is no magnification. On a Telrad, it has 3 rings. You can't really see them here, but the inner ring is a ½ degree, then the middle ring is 2, and the outer ring is 4. And some books with maps actually have telrad circles on them. That's a 4-degree circle, and that's a half-degree circle. Okay, some reflex sites have a single red dot, and I brought one here to show. This is a red dot finder. This is actually a reflex finder on this telescope, but it has 2 rings, not 3, like a telrad, but it is similar in that it has rings. Now, red dot is okay, but what does it do? It projects a single dot, and the dot covers the very target you're trying to point the scope at. That's why the rings are better, is because you put the target inside the ring, you see. And a lot of times scopes come with a red dot. That's how I have this. And what do? I take it off and put it away to use as a demonstration, and then get one of these with a circle. I love reflex finders. I like them. I can hardly use a regular finder scope anymore. I use them on all my scopes now.
Jeff?
This is called a Rigel brand. Yes, Doug?
Some red dots have circles or a circle in the middle as reticles. They give you different reticles.
Okay.
And you don't have to have a dot on your target. They have something with a circle but they're still not as good as a telrad.
Yeah, but anything, I mean, I wouldn't even call that a red dot. I would call that a red circle. But the big disadvantage of all reflex finders is that they don't magnify. So if you're not real familiar with the sky, you will not, you know, the thing about using the reflex finders is if you're hunting for a faint galaxy or nebula and there are no guide stars, if there are no stars like these stars nearby, it can be more difficult than with a regular finder scope that does magnify. But I find that I can use them to find things quite easily. Now, some people use laser pointers as finders, and I've done that. I did that quite recently because I've left my telrad at home, and all I had was my laser. In fact, I have one here, and I use this to turn it on. I don't want to shine it in the camera, but you can see the laser. But the real nice thing about laser pointers mounted on your scope is to show others where the scope is pointed. So you can use them to show when people say, well, what are you looking at? Well, here's what I'm looking at. Okay, I'm close to the end. Some suggestions. I just want to warn you, some things are hard and take a bit of time to master. However, I think the rewards are really worth the effort. One of the most important things is to dress appropriate for long-term comfort and join a community. Become a member of VBAS or hook up with other observers to share your views and share your experience with them, find out what they know, teach them what you know, and have fun. You're going to want to continue the effort if you relax and enjoy it. If you get stuck finding things or setting up your scope, it can be very frustrating, and there are a lot of good telescopes on the used market around February and March after people get these things at Christmas and then can't figure out how to use them. One thing I warn people is never underestimate the power of the cold. Now, my recommendation is to dress for 10 to 20 degrees colder than it actually is. 45 degrees may not sound too cold, but usually we experience 45-degree weather for only a few seconds or minutes at the most. I mean, you go to the grocery store, oh, it's 45 degrees out, I'll take a jacket. Or you go to work in the morning, you go to get the mail, but you don't stand out in the cold in 45 degrees. And 45 degrees without the proper clothes it'll just kill you. So double socks, bring gloves. I have some glove liners that I really like because I can keep them on even when I'm manipulating the telescope. Thermal underwear, hat is always good, boots, layers. Camping and hunting stores, good sources for these kind of supplies. Lose your ego. You may have the nicest telescope out in the field, but if you can't find anything, it's not worth it. It's not worth a darn. So the most important thing is that you be able to set up your scope, find the things you want to find, and have fun in the process of doing it. If all you want to look to, in fact, I've had people tell me, why do you spend all that time outside when you can go online and see pictures from the Hubble? Well, if that's what you're after, I'd say go do that. But it's a far more enjoyable experience to actually be out under the stars, to find things yourself, and to experience a view that is live. This is now. This is what's coming. These are photons that have traveled, in some cases, millions or billions of years to get to you. One of the things I do recommend is if I can find it in binoculars, I can find it in my telescope. If you can learn to use your binoculars as a telescope, it really, actually, I use binoculars more as a finder scope than I do any finder scope. In fact, I don't even have finder scope on any telescope anymore. All I have are reflex sights. And what I do is find the object in my binoculars, and I look for the stars nearby and the relative distances. Oh, this is forms a triangle with these two stars. And then I use the reflex sight to position, even though I can't see what I'm looking for, I know it's there because I found it in my binoculars. This is just more of the same.
Jeff, did you hear about what Dallas is doing?
Dallas,
Texas.
No, what's that?
They're turning off all their lights to reduce the number of birds that pass through. And turning off your lights is a double gift for astronomers.
So we need to coerce the...
Turning the lights off to reduce the birds from coming in, I guess?
Yeah, because they're attracted to light, but the others, you get dark.
Yeah, they run into buildings when the lights are on. It also makes the skies dark for amateur astronomers.
Okay, I've got several targets for this week. The planets, Jupiter and Saturn, are still in great position. Don't miss out. They're going to be around for another month or so. I've got some times that the Great Red Spot transits, which means it's right in the middle of the planet. But I recommend trying to hit the Ring Nebula, Alberio, a double star, and then M15 is the challenge object for this week. And constellations to identify are Cygnus and Pegasus. Let me go on now to show you. This is the Ring Nebula, and this is actually the type of view you can see through a telescope. So you'll see a field of view about like that with the ring about that size.
Tiny, tiny. But sure, it looks just like that.
Just like that?
Yeah.
Without the color, though.
Correct. Okay, without the color. So here's a different look at it.
A good way to find the ring is you find these two stars in Lyra and set your scope about halfway between them, and usually the ring pops in right around the halfway point.
That's correct. It is actually one of the easier targets to find because this is Vega, the brightest star out right now overhead, the brightest star overhead. And this is Lyra, and we talked about it a little bit last week. And this is the second brightest star in Lyra, and this is south, you know.
Why is eyes in two different colors?
Two pictures.
Okay, actually, I think I have a, well, this is a color image here, and then this is a black and white image. But
this is one of our first S-Big images, I think.
So the red, I just recently learned is nitrogen. I always thought the red was hydrogen, but the red is nitrogen. The blue, I believe, is oxygen, right?
Mm-hmm.
And then there is a hydrogen. There's actually a fairly large but extremely faint, you cannot see it visually, globe of glowing hydrogen out much larger.
All right, in the interest of time, I'm going to cut us off right there on this one. Jeff is online. Does anybody have any questions for Jeff?
Well, I see one question that's come in. What about zoom eyepieces? I personally don't own any zoom eyepieces, and they're pretty good. I've used them before because, of course, you can put them on long focal length to find your object and then zoom in on it. I don't know much about the optical quality of zoom eyepieces, but I think if you pay enough money, you'll get a good enough eyepiece. Any other questions?
All right, well, thank you very much, Jeff. Those were two excellent presentations. I think very helpful for certainly newish people to amateur astronomy, but also some of us who've been around for a while. I think we learned a couple of new things too, and certainly some things to think about when we're choosing instruments to buy for our next. I'm not quite up to 5 telescopes yet, but I'm working my way there, Jeff. So we'll another minute.
Have a telescope making class, and you can make a telescope.
Oh, that'll be fun. We've got a couple minutes until our next session. I want to kick it off right around 5. So if anybody's got any conversation or questions further or something you want to discuss, we got a couple minutes.
So are we taking a break here, Eric?
We've got about 2 minutes. I'm going to stop my recording.